Hello, this is a physics video from Young and Freedman's University Physics. I'm following that textbook. And this is the final section of chapter 21 on electric fields and electric charge. And this section is on electric dipoles. I felt like it would be best pedagogically for me to divide it up into two parts. So this is the first of two videos on electric dipoles. And this particular video is the bigger one of the two on force and torque. Force and torque. I feel like I'm on Jeopardy. Okay, what is an electric dipole? Well, we've already seen electric dipoles in this chapter. An electric dipole is a pair of point charges with equal and opposite sign. So one is a positive Q and the other is negative Q. So that's a dipole. They have to be of equal magnitude. Now, water behaves a little bit like an electric dipole. H2O is water, right? And I'm sorry, I messed up my diagram. The H's aren't of different size. This should be a perfect Mickey Mouse with two lovely ears. O is oxygen and H is hydrogen, H2O. Oxygen's much bigger than hydrogen. Now, oxygen tends to hog the electrons, and hydrogen likes to kind of give away its electrons. Hydrogen's very generous with its one electron. And so what inevitably happens is that even though this is a neutral molecule, it's not an ion, it doesn't have a charge, there is a kind of a polarity that exists across a hydrogen atom. The oxygen side of the atom tends to be just a wee bit more negative, and the hydrogen side tends to be just a wee bit more positive. And we could almost kind of say that in between the two hydrogens, there is a kind of sitting in the middle of space, a kind of positiveness that is diametrically opposite a little bit of negativeness. Now, this kind of charge polarity that the water atom has, it's not that much. The charge only shifts about the length of a hydrogen nucleus. That is about the width of a proton. That's really small. And so it's not a very big shift, but we have a kind of a dipole moment, and that's what this P is. There are too many P's. You've got P for pressure, you've got P for momentum. Now we've got P for dipole moment. Anyway, there is a kind of dipole moment from the negative toward the positive, P, that is created by this polarity within the water molecule. Now, this is, even though this may seem like a little, a big whoop, who cares? This is why things dissolve. Ions dissolve in water because the positive ions are just a little bit more attracted to this side of the water, and negative ions are attracted to just a little bit more on this side of the water. And what this does is this kind of slight polarity within the water molecule causes a realignment of ions in liquid. This is why things dissolve in water. And of course, if things didn't dissolve in water, we would not be here. Biological things would not happen. There would be no life of the sort we have on the planet, because all of the life on the planet Earth requires water in the mix. And so it's kind of like, well, wow, what would have happened if this universe didn't have this polarity? And you could use that as part of what's called the fine-tuning argument for the existence of God. Of course, the atheist would say, well, it's the anthropic principle, Ken. We simply wouldn't be here having this conversation if it weren't that way. And so it's pointless to say, well, what if it had been different? It wasn't. Anyway, they're a little philosophy for us. Let's keep going. So what is the net force on a dipole? Well, the net force of a dipole from I should have said uniform electric field. So let me just stop. Okay, now I feel better. Kind of an electric field that's nice and straight, and there isn't curviness to it, and there isn't different magnitudes to it. So if the electric field, if all the lines are going in the same direction and are all the same magnitude, then the net force is going to be zero. If you remember, the force of an electric field on a point charge is the amount of the charge times the amount of the field. Or in vector language, for example, the positive force or the force of the positive dipole is going to equal Q times the electric field vector. And then the negative force on the negative particle is going to be negative charge times the field. Remember, the positive line of force goes away from the positive, and the actually, I probably should have, anyway, never mind. Look at the diagram in the book. But basically what I'm saying is that the forces cancel each other out. And so you have no net force on a dipole in a uniform electric field. Okay, so that saves some math. But now let's talk about this thing called a dipole moment that we've mentioned. The dipole moment is the charge times the distance. So the dipole moment, vector P, is going to equal the distance between the 2-point charges times the amount of the charge, which is Q, let's say. And so that's what a dipole moment is, and we call it P. And it moves from negative to positive. Now, okay, so that's what a dipole moment is. By the way, I have a video, a chemistry video on electronegativity and that sort of thing. And there's a small part of that video on a dipole moment. And I'll link it if you follow the link in YouTube to the landing page for physics, I will link to my video on dipole moments in chemistry. So if in Young and Freedman's university physics, they use P equals QD, dipole moment equals charge times distance. The chemistry textbook, Brown, LeMay, Burston, that I use, this chemistry, the central science, uses this formula. It's the same formula where mu, the Greek letter mu, stands for dipole moment, which makes sense because mu is m and moment, and then q is q, and then it uses r for the distance between them instead of d. But anyway, so you're going to get this in chemistry as well, the dipole moment, and also the Greek, the small letter delta in Greek, the small d, delta plus, delta minus, is sometimes used to label. So for example, in our water molecule, this would be delta minus, and this would be delta plus. Anyway, okay. So back to this video. So you might remember from chapter 10, that was a long time ago. That was like 11 chapters ago. If you remember from chapter 10, tau, which means torque, equals the force on something times the lever arm. So the lever arm here is this perpendicular here. And it's basically the hypotenuse, d, times the sine of phi, or sine of phi, however you want to say it. So this length here is the L lever arm, okay? So if the force is QE, remember from the previous slide, QE is the force, not Star Trek, not Star Wars, I mean. Cardinal sin right there committed. So if the force is QE, the charge times the electric field, and the lever arm is d sine of phi, there we have it. So now we have what the torque is on this thing. Because if you think about it, you know, if this were water and you had two things like this, you know, it's going to, well, which way is it going to go? Well, that's a good question. And we use the right-hand rule, right? And so if lines of force go from the positive, and I hope this is showing up correctly in the video, I think it is, that well, actually, I think it's probably the opposite. But basically, if you have, I think this is for the mirror image, if the lines of force are going from the positive around to the negative, then the thumb points in the direction of the torque, which is into the screen, basically. If you take your hand and do it, it'll be right. This is the way for me to do it, from the positive to the negative, and it points into the screen. But I think for you, this is probably the way I have to do it for it to be right. So from the positive toward the negative, it's going to point into the page, as it were. Remember that, chapter 10? That was fun. And so torque equals force times the lever arm, which is the same as QE for the force and D sine of phi for the lever arm. And then we could do a little shuffling, because remember, what is QD? QD is P. So we can take the Q and the D out and substitute P. And then there's the E sine of phi. And this is basically the vector product of dipole moment times the electric field. Why? Because when you take the cross product of two vectors, you multiply by the quantity E and the sine of the angle between them, right? And so we've got PE, physical education, we're going to work out here. Anyway, no. And then sine of phi. So we can say that the dipole or the torque caused by an electric field on a dipole is going to be the cross product between the dipole moment and the electric field. Okay, a little complicated, but you know, ours is not to question why. Ours is just to memorize or die. Now, the dipole wants to align. I mean, it wants to align with the electric field, and it wants to go in the direction of the electric field. If it's flipped and going in the 180 degrees, it's still, if it even gets slightly out of skew, it's going to flip, and you're going to have an increasing potential energy. The more the torque is in the flow of the electric field. So when we talk about the potential energy of a dipole, again, back in chapter 10, the infinitesimal change in work equals the torque times the infinitesimal change in the angle. Well, we now know what tau is. Tau is well, first of all, the opposite of work is the potential energy. So that's where the negative comes from. So negative PE sine of phi, we know that from the previous slide, right? PE sine of phi, right, there it is. So we substitute that in for tau, and then we have d phi. And so now if we do the integral of it from phi 1 to phi 2, we're going to get the work done. We're going to get the work done from phi 1 to phi 2, or phi 1 to phi 2, if we take the integral of this. Well, the integral of the sine of phi is the negative cosine of phi. And so this resolves into PE cosine phi 2 minus PE cosine phi 1. All right? Okay. So that tells us that the potential energy of phi is basically the negative of this, the negative dipole moment dot the field, because the dot product does, if the cross product is the sine of phi, the dot product is the cosine of phi. And so here is an equation for the potential energy of a dipole in a electric field. Okay, let me think for a second if there's anything more that I need to say. Okay, one correction to make. The reason why the potential energy is negative is because potential energy is the opposite of the work done. Work is active, it's kinetic. So potential is work that could be done. And so that's where this negative sign came from. The reason why this is negative is because torque always wants to decrease the angle of between the electric field and the dipole angle. It always wants to diminish that, and so it's always wanting to go in a negative direction. So that's why that's negative. Okay, well, this has been a little bit of math in this particular one. There'll be a little bit of math in the final one, but this is a video on electric dipoles.